This chart plots a strict binary outcome, like whether a patient survives or dies, against a predictor like age. If we try to fit a standard, straight, linear regression line through this data, we immediately hit a wall. Because the straight line extends indefinitely, it eventually outputs probability values below 0% on one end and above 100% on the other. Those numbers are mathematically meaningless for a probability. To fix this, we bend the line. By shifting to an S-shaped logistic curve, the model strictly binds all predicted outcomes between 0 and 1. This slide shows the math generating that curve. Instead of modeling raw probability, logistic regression models the log odds of the outcome. The steepness and direction of the curve rely on the beta 1 coefficient. Because log odds are entirely abstract, the primary task of a biostatistician is translating this equation back into human-readable risk. Translating coefficients begins with this equation. A beta 1 of 0.042 lacks intuitive meaning. Exponentiating it calculates the odds ratio. An OR of 1 means no effect. Above 1 indicates increased risk, while under 1 signals a protective effect. E to the power of 0.042 is 1.043, increasing odds by 4.3% per year. For someone 10 years older, multiply the coefficient by 10. E to the 0.42 yields a 52% increase in odds. Unlike linear regression, logistic regression relies on maximum likelihood estimation, asking which numbers make our observed data most probable. MLE tests potential parameters, continuously calculating this log likelihood equation until it locks on to the tightest fit for the data. MLE executes the heavy mathematical lifting to shape the curve and identify the coefficient. We then exponentiate that value to extract an odds ratio that makes sense in clinical practice. 5 variables predict HIV status well. Adding 15 more creates noise, causing the model to memorize random variations, known as overfitting. Instead, use metrics. An AUC of 0.79 shows good discrimination. For Hosmer-Lemeshow, a p-value above 0.05 is the goal, confirming excellent data fit. A rigorous multivariable model is validated by strong evaluation metrics like AUC and likelihood ratio tests, not by maximizing the number of predictors. In biology, variables rarely operate in isolation. The effect of one predictor often depends on another, a dynamic called interaction. To account for this, we multiply the two variables together as a new term, forcing the model to adjust the slope. The analytical workflow follows a strict sequence. You build the equation in log odds, calculate predicted probabilities, and isolate the effect size using the odds ratio. You then verify findings using the Wald statistic for individual predictors and log likelihoods for overall fit. By translating log odds to actionable odds ratios, biostatisticians gain a consistent method for analyzing binary outcomes and identifying the drivers of clinical risk.